This video presents a method to reduce the computational effort in magic square enumeration by approximately half using the concept of complementarity in magic squares. The complement of a magic square of order n is obtained by replacing each element I with n squared plus 1 minus I. The result is guaranteed to be a magic square. Since applying the complement operation twice returns the original magic square, the complement transformation is expected to form pairs of magic squares. If we enumerate only one instant from each pair, omitting its complement, enumeration effort seems to be reduced by half. However, this naive expectation does not always come true. Here is an example of a magic square of order 4, which exhibits a certain symmetry. If we take its complement, we obtain this one, which happens to be a rotated result of the original. In this case, the complement doesn't produce a distinct pair, but instead maps the magic square into its equivalent. In addition to rotations, reflections and M transformations also play important roles in magic square enumeration. We therefore need to handle correctly the cases in which the complement transformation coincide with another symmetry transformation. In the following, we refer to any combination of rotations, reflections, and the M transformations as an RFM transformation. The RFM transformations defines equivalence classes in the entire set of magic squares and reduces the enumeration problem to counting these equivalence classes instead of individual magic squares. If you are unfamiliar with the M transformations, please refer to part 1 of this video series for its introduction. We should recognize the RFM transformations and the complement transformation are quite different in nature. The RFM transformations are position-based and the complement transformation is content-based. These two types of transformations are independent of each other. In fact, they commute. More precisely, for any RFM transformation E and the complement transformation C, the compositions EC and CE yield the same result. This property leads to an important lemma. The complement of two equivalent magic squares then self-equivalent. Therefore, the complement transformation always maps an equivalence class of magic squares to an equivalence class. Moreover, since the complement transformation is reflective, it defines pairs of equivalence classes, except in cases where the complement of a class is identical to the original class. To take advantage of complementary pairing in magic square enumeration, we must detect the self-complementary cases and also find a way to select exactly one instance from each complementary pair. However, implementing such an exact algorithm efficiently appears to be difficult. Instead, we relax the condition and define a broader category that fully contains all self-complementary cases. With this category, we count exactly half of magic squares outside it and count all of them without omission inside it. If the size of this broader self-complementary category is small enough compared to the entire set of magic squares, the efficiency of the enumeration can improve by approximately a factor of 2. As a means of implementing this idea, we introduce a weak ordering on magic squares. A weak ordering is a generalized ordering that allows ties in addition to the usual greater than and less than relations. It can be viewed as a kind of ranking, in which multiple objects may share the same rank, while objects in different ranks are compared based on their rank values. To detect self-complementary cases correctly, we define the ordering so that all magic squares within the same equivalence class have the same rank. We then define the broader self-complementary category as the set of magic squares whose complements lie in the same rank as the originals. When the rank of the complement differs from that of the original, we can select exactly one instance from the pair according to the rank difference. The enumeration rule is as follows. If the complement transformation decreases the rank of a magic square, count it as 2. If the transformation increases the rank, omit the case entirely. If the transformation preserves the rank, count it as 1. The optimal choice of ordering depends on the specific enumeration procedure and is to some extent ad hoc in nature. In this video, we present two examples. One is a well-known method applicable to odd orders, and the other is the method I used in the enumeration of 6x6 magic squares, which is applicable to arbitrary orders of either parity. The well-known method for odd orders defines the rank of a magic square by the value at its center. Since rotations, reflections, and M transformations never change the center value, this ranking satisfies the requirement we discussed earlier. The complement transformation maps the center value from I to n squared plus 1 minus I. If the center value is equal to the half of n squared plus 1, the magic square belongs to the broader self-complementary category. Otherwise, there are exactly two possibilities. The rank of the complement is greater than the original rank, or it is smaller. We consistently select only one of the cases and omit the other. If the enumeration is performed by choosing the center element first, this ordering provides the most effective pruning. Simply enumerate magic squares for center values from this to n squared, then multiply the result by 2, and add the result for the center value n squared plus 1 over 2. This method is easy to understand and can be implemented efficiently. However, it depends on the existence of the center position that is invariant under the RFM transformations, something not available for even orders. For even orders, we can introduce an ordering based on the greatest row set or column set. For the definition of row set and column set, as well as the ordering between these sets, please refer to part 1 of this video series. Since any RFM transformations consists of rearranging rows and columns and never change the membership of each set, the greatest row or column set remains invariant under the RFM transformation. Therefore, this ordering is suitable for our purpose. In the following, we denote row set and column set simply as row and column, respectively. How efficiently this rule can be implemented depends heavily on the specific enumeration procedure. Let us recall the procedure we adopted in the Part 1 video. We generate combinations of rows and columns which satisfy these constraints. It should be noted that R1 is always the greatest of all rows and columns as a result of these constraints. To exploit the complement transformation in the enumeration, the procedure is modified as follows. Here we introduce a new notation, the tilde, to denote the complement of a row or column. A tilde is a set of n integers obtained from A by replacing each element I with n squared plus 1 minus I. This is not the complement in the set theoretic sense, so it should not be confused with it. A magic square is eligible to be counted only if its greatest row or column is greater than or equal to the complement of every row or column. So as the first step, choose an R1 which is greater than or equal to R1 tilde, and save the value R1 tilde for later use. Then remove from the candidate list for all subsequent rows and all columns any members whose complement is greater than R1. These steps are sufficient to remove all cases that should be pruned. The remaining task is to determine whether the increment should be 1 or 2. If R1 is equal to R1 tilde, then the increment is immediately set to 1. Otherwise, the determination is postponed. Each time rows or column is chosen, check whether it is equal to R1 tilde. If it is, the increment is set to 1. If the increment is still undetermined after all rows and columns have been fixed, then the increment is set to 2. At this point of configuration generation, the pruning and the determination of the increment are completed, and the remaining tasks of generating diagonal candidates and detecting magic squares can be performed without any overhead. Moreover, in the case of an even order, we can prove that any column cannot be equal to R1 tilde, although the proof is not so obvious. Thus, if we fix all rows first and then fix the column later, the increment determination process will be removed from the deeper levels of the program. Consequently, the overall overhead becomes vanishingly small. Although the pruning procedure works optimally, there is a room to improve the method by shrinking the broader set complementary category. Specifically, in the case R1 is equal to its complement, there are many magic squares that are actually paired by the complement, but which we counted individually in the procedure just described. We can introduce a subordering based on R2 within this subgroup of magic squares and reduce the enumeration effort further. In this video, we have discussed the general scheme to exploit the complement transformation in the magic square enumeration, and have proposed a promising implementation which reduces the enumeration effort by almost half. There are still many details and techniques not explained here that were essential to making the enumeration of 6x6 magic squares feasible. For those, please refer to the sequel videos. Thank you for watching. See you then.